All right, hello, folks. So we are trucking along and starting chapter 8 this week. Much of this lesson relates to issues of probability. Probability is used to determine the degree of confidence we have in stating a particular finding is true, or that an outcome is not simply due to chance. And understanding the normal curve is a really critical part of doing probability, as we'll see over the next couple of chapters in this course. So normal curves or bell-shaped curves, we've kind of looked at these so far in comparison to ones that might be leptokurtic or mesokurtic or platykurtic. But what are some more of the technical details about a normal or bell-shaped curve? For it to be a legit full-on normal curve, there's three characteristics that it has. So the first one here is that the mean, median, and mode are all equal, that it's the same value for the mean, median, and mode. And you'll remember back from chapter 4 that if the mean and the median are different, then the distribution is skewed one way or another, right? Either it has more of a positive skew with values lumped down here, or it has more of a negative skew with values lumped at the high end. So first characteristic, mean, median, and mode are equal. Second characteristic is that it's perfectly symmetrical around the mean, that one half of the curve is a mirror image of the other. So you can think about this as if you had this piece of white paper that's in this graphic here and you folded it in half right along the mean in the middle, both sides would be perfectly matching, right? That it's symmetrical around the mean. This half is exactly equal to this half, 50% of values on both sides. Characteristic 3 then is that the tails of the curve are called, here's a fun word, asymptotic. This means that they come closer and closer to this horizontal axis here, but never actually touch it. This means that there's always a very small likelihood that an extreme score exists, an extreme score at the low end or an extreme score at the high end. Even if they touch the line, then the extreme scores would be capped off at some point, right? So an asymptotic tail means that they come closer and closer to here, but never actually reach this 0 point. Other way that's often used to conceptualize this is if you fold a piece of paper in half, then in half again, then in half again. You can do this over and over again, and the paper will continue to get smaller and smaller, but it will never actually disappear into nothing, right? That's very much this idea of the asymptotic tail, that it goes on for infinity that and never actually reaches the 0 point. So that's the idea of the normal curve. Okay. I have to include this here. Normally, when I teach this class, when we're not starting the semester 2 weeks early, like we did this year for COVID, we're like right at Halloween. So this is, of course, a normal distribution, and here's a paranormal distribution. He, he, he. Okay. All right. Something else important is this idea of large samples and a normal curve with large samples. So when we have a large enough data set and we take repeated samples from a population, most variables will end up with a normal curve if we have taken repeated samples. So if you do something enough, most things will start to look like a normal curve. The reason that this is so important is because when we use a sample to make inferences about a population, we assume for all of this, most of the statistical analyses we'll be doing, that the sample and the population are normally distributed, meaning that if we chart it out, we did like our histogram and then our polygon on top, frequency polygon over it, that frequency polygon is gonna look like a normal curve. So if I was going to give an example of this, perhaps we wanted to study what are average dropout rates at high schools nationwide. And so we would take a whole bunch of samples, right, from different high schools. One high school could have a mean dropout rate of 40%. something really high. Other schools might have a mean rate that's really low, like at 1%. But the majority of schools would have mean rates right around the national average at 7%, right? So this, if we took enough samples of different high schools, the distribution is going to end up looking like a normal curve. And that's this idea of large samples. We could not just, for example, or in contrast, take a sample of one or two different high schools and have a sense of what is the true average dropout rate for the entire country, right? We would need to take all of these large samples. And as we do that, this would begin to approximate the normal curve. So this is, if you're looking in the text too, there's an example that's helpful on this starting around page 152 that helps to explain this. But another example of this idea of large samples is if we were studying, for example, how smart people are, right? There's going to be some people, if we sampled, who are not so smart, but most people are going to be in the middle here, right? People who are moderately smart. Then there's going to be some people who are really, really smart and have high intelligence scores, or however we're measuring this, right? But that if we took enough samples of different people, it's going to approximate a normal curve where it's the moderately smart people occur the most and the people at other ends of the extreme the least. You could do the same thing thinking about a variable on height, right? Most people are kind of average height. There's some people who are super tall, some people who are super short, but most people are in the middle, right? This is this idea of normal curves with large samples. I would normally, let me say now, normally when I teach this class, I take a pause and we do an activity that's based off of coin flipping. And so I have everyone flip a coin 10 times and determine out of those 10 times, how many times do you get a heads versus a tails, right? And if we do that enough times, our average should come out to about 50% heads, right? That we know there's a 50-50 chance of getting heads when you flip a coin. And if we have enough samples, enough students do it enough times, our overall class average is going to be close to 50%. But is there always one student who gets lucky and flips the coin and gets 9 heads out of 10? Is there always one student who gets really unlucky and flips the coin and only gets 1 heads out of 10? Yes, but the majority of people get close to this 50%. So if I will just briefly describe that now, it's hard to recreate in an online setup, but hopefully that kind of gives you another example of this idea of, if the sample is large enough, we're going to start to begin to approximate a normal curve. A couple of real world examples for this. These are kind of fun to think about. So the first one here for weightlifting is that the wear pattern. So if you've used this type of weightlifting machine, you know, you put the little pin in for how much weight you want to be lifting. And so the wear patterns show exactly what we'd expect a normal distribution to tell us about how much weight people put on, right? It's more people are using the machine at the middle weights. Are there some people who are super strong using it down here and some people who are not so strong at all and using it up here? Sure, but the wear patterns show that most people are using it in the middle. Another example related to retail, especially grocery items. Because stores like to keep the most popular products together and right in front of your face, the business maxim for this is eye level is buy level. You buy things more when they're right at eye level. So stores tend to stock things in a normally distributed pattern with the really popular stuff right in the middle and the less popular stuff up high or down low. So the most popular items are in the middle. And so when there's, especially when there's like, I don't know, a pandemic or, a snowstorm coming or something like that, or a big sale and stores don't immediately restock, you can really see this idea of a bell curve emerge, that the most empty shelves are the ones in the middle and the fewer empty spots are the ones at the opposite ends of the spectrum. So hopefully that's kind of helping to put in perspective the normal curve as well. Okay, now, so that's kind of the conceptual stuff about a normal curve. Now, big deep breath, woozah, we're going to transition into the actual math part of this. I'm going to warn you that some of what we cover in this chapter on the part that's on z-scores is probably one of the hardest things we do all semester, that can be the most challenging for people to get. And so I don't say that to scare you, but to say plan accordingly for how much time you will devote to this lesson this week. But I have every amount of confidence that you guys are going to do a kick-ass job and learn z-scores and will be great at them. But they take a little time, they take a little practice, and can be challenging to figure out at first. So know that I am here to help. We'll do lots of practice and get through it. But if you need now a big woosah breath before we get into the math part, here we go. Okay. So what's really key about the normal curve is that statisticians way smarter than me or you have figured out certain characteristics of the normal curve that apply all of the time. And so we can think about how the mean and standard deviations can be used to understand the probability that a certain value occurs. And so kind of just as a conceptual starting point, so we know what we're looking at, perhaps we had a normal distribution of, this could be anything, let's say test scores, with the mean test score being 100. The mean is always in the middle for a normal curve. And then we can count out if this was a distribution with a mean of 100 and a standard deviation of 10, we could count out how many standard deviations below and above the mean we fit in, right? So if this distribution had a standard deviation of 10, we would know that one standard deviation below the mean would be 90. Two standard deviations below the mean would be 80. Three standard deviations below the mean would be 70. Same thing above, right? If this distribution has a standard deviation of 10, one standard deviation above the mean is 110, two above is 120, etc. Why this matters is because for any distribution of scores, any normal distribution, regardless of what the mean or standard deviation actually is, almost 100% of all values will be within 3 standard deviations from the mean. Almost no values will be beyond 3 standard deviations from the mean. So what is being represented here is that the reason that the normal curve is so important, I would say so cool, is because if it's a normal curve, statisticians have figured out that always about 34% of all scores are one standard deviation below the mean, and about 34% are one standard deviation above the mean. Always about 48% of the scores are 2 standard deviations away from the mean. So this 48% comes from approximately this 34 plus 13, right? That approximately 48%, almost half, fall within these 2 standard deviations above the mean, right? And this is the same on both sides, because we remember that the normal curve is perfectly symmetrical, that 50% of all values are on one side of the mean and 50% of all values are on the other side of the mean. And so thinking about this already, if you are into like sports betting, your mind should be turning, knowing that if you are looking at something that is normally distributed and you know the mean and the standard deviation, you can know that almost never is there going to be a value that is greater than 3 standard deviations above the mean or below the mean, right? That this is only 0.13% of all values is outside of 3 standard deviations from the mean. So this is really the basis for everything we're going to do the rest of this chapter on what are called z-scores. And so this is just another way to visually look at how these values break down. That if we're looking here, that this is, these numbers here are standard deviations from the mean. And again, it doesn't matter what the actual mean is or what the standard deviation value, how big or little it is. Always, 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 one standard deviation below the mean is going to be 34% of values. One standard deviation above the mean, 34% of all values. And so these numbers on the bottom are just showing the combinations of within one standard deviation of the mean, either below or above, is about 68% of all values, right? That's the 34 plus 34. Always, always, always within 2 standard deviations of the mean is over 95% of all values. And within 3 standard deviations is nearly all values. Over 99% of all values are within 3 standard deviations of the mean. So this is commonly referred to in statistics as the 68, 95, 99 rule of normal curves, right? That we have this as always, always, always. This is how many values exist within a certain number of standard deviations away from the mean. And so why this is important is because this is also about the probability that a certain value would exist, right? The probability for a value to exist that is outside of 3 standard deviations from the mean is really, really small. Okay, so this idea of the number of standard deviations away from the mean can be captured also by something that's called a z-score. So a z-score is essentially a value that's adjusted for the mean and standard deviation of the distribution from which the raw score comes. So essentially a z-score is how many standard deviations away from the mean is a given value, right? And so if, for example, we were going back to this example, we would say that 90 here, this is the, remember the distribution that has a mean of 100 and a standard deviation of 10, a value of 90 would have a z-score of -1 because it's one standard deviation away from the mean, right? So a z-score is essentially just what's the number of standard deviations away from the mean a given value is. A value of 120 here would have a z-score of 2 because 120 is 2 standard deviations away from the mean. There's a formula to actually calculate a z-score for any given value. And so X, as always, remember, is our statistical notation for the individual score we're looking at. In the example we were just doing, it would be that 120 or the 90, right? What's the number we're trying to find for how many standard deviations that number is away from the mean? That's our X. And then our X bar, as always, is the mean, and S is our standard deviation. And so the reason that z-scores are important or are cool is that it allows us to compare values in different distributions. It's kind of like a standardized score to look at how far different values are from the mean. And to illustrate this, here's again what I miss, especially for the z-scores unit, I get to use on the whiteboard usually all my fun different colored markers. As you'll see, there's a lot more of the color coding, but here instead, my son is getting annoyed because I'm borrowing all of his colored pencils to be able to do this lesson online instead. But okay, so let me illustrate this point about how z-scores are essentially standardizing how many standard deviations a given value is. So on the left here, we have a distribution that has a mean of 100 and a standard deviation of 10, right? That's very much just like the other example we looked at. We know, so this first row here is just that what are the different values, right? That here 100 is our mean, so that's in the middle. And then we can count out how many standard deviations away from the mean we are, right? So one standard deviation below the mean, because our standard deviation is 10, would be 90. Two standard deviations below would be 80. And so the second row here are our z-scores, right? 130 is 3 standard deviations above the mean, so the z-score is 3. Over here, though, we have a different distribution in which the mean is 20 and our standard deviation is 5. So with a mean of 20 now, 20 goes in the middle, and we can count out 5 values below 20 would be 15, right? Here our standard deviation is 5. So one standard deviation below the mean would be 15. 2 below the mean would be 10, right? 20 minus 5 minus 5, that's 2 standard deviations below. And so again, here we see the z-scores in this row are representing the number of standard deviations away from the mean any given value is. What is cool about this is now we can compare distributions, even though the means and standard deviations for these two distributions are different. We can say, for example, that 30 is the same number of standard deviations away from the mean here as 120 is from 100 in this distribution, because both have this z-score of 2, right? They share this concept that both values are 2 standard deviations away from the mean. So when I say that a z-score like standardizes values, what that means is we can say across different distributions, if a value has the same z-score, that's consistently telling us how many standard deviations away from the mean that value is. A little more just kind of background on z-scores. Any raw score, and so when I say raw score, individual score, that's referring to these, right? What are the actual values within the distribution, not the z-scores. Any raw score that's above the mean, so up here above the mean, will always have a positive z-score, and any value, any raw score that's below the mean will always have a negative z-score, right? The negative tells us how many standard deviations below the mean. A positive z-score tells us how many standard deviations above the mean there will be. Positive z-scores always fall to the right of the mean, right? The upper half of the distribution. The negative scores to the left, the lower half. And the more extreme the z-score is, meaning the higher the absolute value, the farther it is from the mean, right? So we can say z-score of -3, comparing this value of 5 to 25, that has a z-score of 1. 1 is a higher value than -3, but we know 5 is farther away from the mean than 25, right? So it's the absolute value, meaning Absolute value means don't count the negative. 3 is bigger than 1. So we know that 5 is farther away from the mean than 25. Okay. So we can do a couple of these problems before we even use much of the harder math. So we'll start with thinking about this conceptually, just knowing what we know about the area under the curve, right? And so thinking about this as probability, we know that 84% of all scores would fall below a z-score of 1. There's 50% of them below the mean, and then there's this 34 here, right? And so if I was going to draw this out visually for myself, we would know that half of values, all of those that are below the mean, are 50% of all values, right? Because the normal curve is perfectly symmetrical, there's half on each side, that there's 50% here, and within 1 standard deviation of the mean is 34 values, right? 34% of all values. That comes from this. Again, this is statisticians over the years have figured out that this is just always, always, always the case for a normal curve. The reason the normal curve is so cool is because this is always the case, regardless of what the actual mean is or what the actual value of the standard deviation is. Always, always, always 34% of all values fall within 1 standard deviation of the mean. So that means that we know 84% of all values, 50 plus 34, would be between nothing and 1 standard deviation above the mean. This also then means or indicates that 16% of all scores fall above a z-score of 1, right? So that if we're looking at what we just did with this 50 plus 34, how would we know what's the likelihood that any given value would be above a z-score of 1? Is there's a couple ways to figure that out, right? If we know that 100% of all values are under this curve, right? Are in the distribution is 100% is everything, right? All values underneath here is 100%. And we took out this chunk that we just figured out, this 84. 100 minus 84 would leave us 16% of all values here, right? Or another way to do it is that we know that on this side of the curve, everything above the mean is 50% of all values, is in this orange and green combined is 50%. And if we want to know what's in this green part, and we know that this orange is 34, if we take out 34 from the 50, that leaves us with 16, right? So whichever way makes more sense for you conceptually, think about it like that. Okay, so this is all kind of just explaining kind of conceptually how we can figure out the probability that a certain value appears or doesn't appear. So if we were going to do this as an actual problem, and this part here seems like very straightforward, I hope we'll get to ones that are a little more complicated. So I say that to say, if I'm breaking down all of these steps now and you're thinking like, oh, I don't need to go through all of these steps in order to get the answer for these first ones, do the steps, because the later problems get a little more complicated, and then you definitely need all of these steps. So for when we do the problems in this chapter, I will always give you, in a given example, what is the mean and what's the standard deviation. And then I ask you, what's the probability that any value will be somewhere under that normal curve? So this first example problem, this first practice problem is, we have a distribution with a mean of 100 and a standard deviation of 10. What's the probability that any one score will be 110 or greater. And so when we do these, there's 4 steps to go through. The first step is you're drawing the curve and putting in the mean score that you're trying to find, and then shading in the area you're trying to find. I know this sounds silly that we're doing these little pictures. Trust me, you cannot do these more complicated problems without drawing the curve and shading it in. It's brain just requires that. Then you calculate your z-score and identify the area under the curve associated with that score. So let's do that. So for this problem with a mean of 100 and a standard deviation of 10, what's the probability that any score will be greater than 110? Step 1, you draw your curve like this, right? So draw something that approximates a normal curve. Put your mean in the middle. So the mean was given to you as part of this problem. Put in the value that you're trying to find. Here it's 110. That comes from this part of the question, right? We're trying to find the probability that any score is greater than 110. So first step is to just draw your curve, put in the mean, and put in the individual score we're trying to find. Step 2 is shade in the area that we're trying to find. Here, this question asks, what's the probability that any one score will be 110 or greater? So if it's 110, we're shading in above this, right? This is greater is to the right, less than is to the left. So that if this problem instead said, what's the probability that any value is less than 110, we would be shading everything over here, right? But so you're shading in the area that you're trying to find. Here we're trying to find everything that's greater than 110. Then calculate your z-score. So remember the formula for z-score is x minus x bar divided by s, where x is the individual value we're trying to find. Here it's 110 minus the mean. Our mean is 100 divided by the standard deviation. Our standard deviation is 10. That was given to us as part of the problem. Do the math on that, and it comes out to a z-score of 1, right? Which makes sense. We know 110 is 10 values away from 100. That's a z-score of 1. Again, these ones are very basic, simple numbers to get started, but practice doing the steps. Okay, so we have our z-score of 1. Step 4 then is to figure out the area we're trying to find. So we know that within one standard deviation of the mean is about 50% of all values is both of these. Everything above the mean is about 50% of all values. About 16% of all values are within one standard deviation of the mean. And so here we know that 34% of all values are greater than 110. We can do a separate example now, getting a little trickier. A distribution with a mean of 50 and a standard deviation of 5. What's the probability that any one score will be less than 40? So again, we go through and do our steps where first step is to draw in our curve, put our mean in, put in the value we're trying to find, and then shade in the area we're trying to find. Here, this problem is asking us, what's the probability that any one score will be less than 40? Here, less than 40, we shade in whatever color you like. Next step is to calculate our z-score. So our z-score here is formula is x minus x bar divided by the standard deviation. Here, the x we're trying to find for is our 40. The 50 is our mean, and a standard deviation of 5 that's given to you as part of the problem. This gives us a z-score of -2. We know from the curve that we have that 47.5% of all values are always within 2 standard deviations of the mean. And so we say, what is this remaining green part then, right? If within 2 standard deviations of the mean is 47.5% of all values, and we know everything that's less than our mean is 50%, we can say take this 47.5 out of the 50. If we remove this orange part here, that's going to leave us with the green. So we know that 2.5% of all values are less than 40. Okay. What if, though, the z-score isn't perfectly 1, 2, or 3? So far, we've just used the perfect z-score of 1, 2, or 3 because we have that curve that I showed you that statisticians have figured out. Always, 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 the 68, 95, 99 rule applies. But what if a value we're trying to find isn't exactly even number of standard deviations away from the mean? Well, statisticians have calculated what's the area between the mean and that z-score for every possible z-score that exists out to 2 decimal places. So in order to do these ones, when you end up with a z-score that isn't perfectly just 1, 2, or 3, and you can't just go back and look at that area under the curve, you need to use this table in the back of your textbook on page 400. I also, if you don't like always having your textbook around, this table is just 2 sheets that I have saved for you as a PDF that's in this module as well. So the file that's right after the lesson handout, the lesson outline, is saved as the z-scores table. You can reference that as well, or just use it straight from the back of your book. But you'll see that this has tons and tons of columns over 2 sheets. And I've just, for illustration's sake, pasted half of one of these sheets in here so that we can see it. But there's one column that's the actual z-score value, and then the column that's next to it is the area between the mean and that z-score. So if you had a z-score that was 0.15, that means that the area between that value for 0.15 with a z-score of 0.15 and the mean is 5.96. Then this gets a little confusing because the next column over just starts the next z-score, right? So, and they kind of, in the textbook pages open up so they're right next to one another, but you would expect, if you're looking at just this on the sheet, you would expect this 0.24 to then go to 0.25 up here, but it doesn't. It goes down onto the second page. So kind of keep that in mind when you're trying to identify values. Like same thing here, right? The 0.74, if we're going in order, you would expect then to be the 0.75 up here. It doesn't. It goes down onto the next page. So if you're, looking for one of the values and get lost, remember that they spread across the 2 pages. And if you're looking in the textbook, that makes sense. The way that it's set up is easier to read. Okay, but so these are just like multiple columns that for every z-score, then it tells you the area between the mean and that z-score. Note that there's no negative z-scores listed here, is because it's area under the curve, so that it's always the same thing, right? That the z-score of negative 110 would be the same area under the curve as positive 1.10 as well, right? So that there's no negative z-scores. You just look at the value for what it would be as negative. If you had a negative z-score of negative 1.2, you would just look here to find the area under the curve for a z-score of positive 1.2, and it would be the same, right? Area under the curve is always positive. Okay, what am I forgetting on this slide? Nothing. All right, so how does this look? So now that we can't just rely on that area under the curve image, and if we have a z-score that's not perfectly 1, 2, or 3, and we need to use the chart, let's do the steps for these ones. So if we had a distribution with a mean of 80 and a standard deviation of 5, What's the probability that a score is greater than 88? First step, always, always, always draw your curve and shade in the area you're trying to find. So we draw our normal curve, we put our mean in the middle. Here as part of the problem, we know that our mean is 80, and we put in the score we're trying to find is 88. 88 is higher than, is greater than 80, so we know it goes on this side of the curve, and we're trying to find what's the probability that any value is greater than 88. So we're shading in this part to the right of that's higher than 88. Step 3 is to calculate our z-score. Z-score formula is always our x, the value we're trying to find here is 88, minus our mean is 80, and divided by the standard deviation. Here is part of the problem. We know for this distribution, the standard deviation is 5. Go through and do the math on this, and we see that this gives us a z-score of 1.6. Now we need to look at that table in the back of the book, or a copy of that is posted into the module this week as well. And we find what's the spot that has our z-score of 1.6. Then we see the area under the curve that's associated with a z-score of 1.6 is 44.52. Here is where drawing the curves and doing the shadings is so important, because this is the most common error that students make with z-scores. The area that's associated with that z-score is the area that's between the mean and that z-score. It's not necessarily your final answer, right? That's why the shading is so important. So once you get the area under the curve that's associated with that z-score, identify on your image where that area goes, right? So because it's associated with the spot that's between the z-score, 88 has a z-score of 1.6, and 44.52% of all values are between this z-score and the mean. This green part is what's the 44.52, right? The area between the mean and the z-score is the 44.52. But we're trying to find what's this red part, right? What's the area or the probability that a value is greater than 88. So how could we do that if we know what this green chunk is? We know that everything above the mean is 50. So if we take this red and green combined, if we know the red and green combined is 50, everything above 80 is 50, and we remove the green part, that's going to leave us with the red, right? So 50, we have to subtract 50 minus 44.52 to get our final answer of 5.48. So we would say that this 5.48% of all values are greater than 88. So in a distribution with a mean of 80 and a standard deviation of 5, we can say that there's only a 5.48% probability that any value is going to be greater than 88. That's what this is telling us. So where z-scores get tricky is that you always have to draw out what is the area that I know and what is the area that I'm trying to find, and then use your own logic and problem solving to figure out, given what I know, how do I find the area I'm trying to find? For this example, the two things that we knew were that everything above 80 is 50% of all values, and we knew that this green area was 44.52%. Knowing that, how can I problem solve to find out what the red is? Okay. Example number 4. In a distribution with a mean of 200 and a standard deviation of 42, what's the probability that a score will be between 85, and 210. So now we're not just doing a likelihood that a score is less than or greater than a certain value, but what's the probability that a score is between two values? So the same steps apply. Always start by drawing your curve and shading in the area that you're trying to find. So you draw your curve here, put your mean in the middle. Your mean in this problem is 200, and say we know we're trying to find the area between 85 and 210. So that we're shading in both of these chunks here as the area we're trying to find. Now we're calculating our z-score for both. 85 is going to have a z-score, right? We're asking how many standard deviations away from the mean is 85, as well as for 210, how many standard deviations away from the mean is 210. So we do our z-score formulas, x minus x bar. First, we can do it for, it doesn't matter which one you do first. If you do 85 first, 85 minus our mean of 200 divided by our standard deviation of 42 gives us a z-score of negative 2.7. Then we do the same thing for 210. 210 minus our mean of 200 divided by the standard deviation of 42 gives us a z-score of 0.24 for 210. Then we look at the tables in the back of the book or on the handout, find our z-score of 2.7. Remember, there's no negatives listed on the table, that we just look at the absolute value. A z-score of 2.7 is 49.65% of all values are between that z-score and the mean. So we know then this purple part is 49.65. Then we also have to find the area under the curve for a z-score of 0.24. Our z-score of 0.24 is associated with 9.48% of all values. So we know this orange part, the area between the mean and a z-score of 0.24 is 9.48. So if this problem is asking us to find what's the probability that any value is between 85 and 210, we know this part, the purple is 49.65, and this part is 9.48. How do we find the two of them together? We add them, right? So if we add the 49.65 and the 9.48, this gives us a final answer of 59.13%. So we say 59.13% of all values are between 85 and 210. Again, the tricky part about z-scores is making sure you are really diligent about drawing your curves and labeling the areas that you know. Then you can use your own problem solving to say, how do I use the information I have to get to the final answer, right? So there's not a steadfast rule about adding or subtracting, or when you add 50, subtract 50. You have to shade in the area that you know and ask yourself, how do I find the answer? Okay, so going through, this is just a couple of practice problems that I'm doing on the slides here together. There's a ton of them that we will do in the classwork. So it's okay at this point, as I always say, if you're coming away from the PowerPoint part and you're feeling meh, or even like, holy crap, I'm really lost for z-scores, that's okay. I promise by the time we work through it, a ton more examples in the classwork, you're gonna feel better about it. So it's okay to be at the meh or not so great stage here. Okay, last thing then that I want to say here, and this is really just starting to plant the seeds of why the normal curve and z-scores matter for more advanced statistics. So I don't expect you at this point to totally get this last slide. The idea is that this is starting to lay the groundwork for why this matters for more advanced statistics. So we know, of course, as we looked at, z-scores really represent the probability or likelihood that a certain score exists within a distribution. And when we start to tie together z-scores and normal curves to everything we did with hypotheses last week, is how do we know, once we start doing the statistical tests, if we should be accepting or finding value in a null hypothesis or an alternative hypothesis. And the way that we do that is whether or not something observed relationship is due to chance. So when testing our alternative hypothesis, if we find that the likelihood of a certain event occurring is very extreme, then we can conclude that the reason for that being really extreme is likely due to the independent variable and not just due to chance. So what counts as extreme is generally less than 5%. So if a actual value falls at that very tail end of a normal distribution, we can say, oh, wow, that's really unlikely to happen because we know the probability of a value being that far out on the curve. So again, this last slide is just conceptual, starting to plant the seeds in your mind for why this matters in doing inferential statistics. The main part for this lesson is being able to do the problems with z-scores and understanding that these certain characteristics and rules always apply for normal curves. So go ahead and take a shot at the classwork problems and check your answers against the ones that I post. Send me questions. Let me know if you want to have a live class this week or have office hours where we do more together. I'm happy to do any of those options. Take care, folks. I will talk to you soon.